the CTO of Fastly. They've experienced tremendous growth recently, and they have one of the most ridiculous workloads that I've heard of. And today he'll be giving us an interesting talk on probabilistic algorithms.
Hi. Right, so like Sammy said, I'm going to talk about algorithms that probably work. I guess this talk would actually be better titled "It Probabilistically Works," or actually even better would probably be "It Provably Works Probabilistically." Although I'm not actually going to get into much math with it because that's not me. I'm not that guy. So who am I? Like Sammy said, I'm the CTO of Fastly. What is Fastly? We're a pretty awesome CDN. We do all the normal things that a CDN does, but then also layer on things like real-time purging and analytics and a whole bunch of other stuff. And that's basically the last I'll say about Fastly during this talk. So what makes me qualified to talk about this? Nothing. Nothing at all. Like I said, I have like no formal education. I am terrible at math, and this is what Applicative gets for letting me talk about anything I want. Okay. That's not actually entirely true. I have written implementations of these algorithms, and I've used them successfully in production. So I do have some experience with it. All right, so what are we talking about? So we're talking about probabilistic algorithms, otherwise also occasionally known as randomized algorithms, and occasionally estimation algorithms. So it's kind of the roadmap. Talk a little bit of theory, talk about like where we could use these, why they're useful, and then go through a couple different ones. I tried to pick 3 different algorithms that were pretty different from each other. HyperLogLog is pretty straightforward. Locality-sensitive hashing is quite a bit different, and Bimodal Multicast is a distributed probabilistic algorithm. So, right. So just to define it, this is an algorithm that uses randomness to improve its efficiency at a very, very high level. And there's 2 major classes of these. The Las Vegas type, which is guaranteed to find the exact correct answer, but has a random element in its runtime, and the Monte Carlo type, which may not find the exact correct answer, but it does have a fixed runtime. And generally, the runtime is also quite a bit shorter than you would be getting if you found the exact answer. So just as a quick example, here is a terrible, horrible example of a Las Vegas algorithm. So we're basically just trying to find the needle in the haystack, and we're just going to loop and pick random indexes in the array until we find it. So obviously this will run for a random amount of time, but it will eventually find it, if it exists. Otherwise, it'll just run forever. And here is a terrible, horrible example of a Monte Carlo algorithm, where in this case we pass in the haystack, the needle, and we also pass in the number of rounds that we want to try to find it with. Right? So in this case, it may not find the needle, but it will take an exact amount of time, an exact and configurable amount of time to try to find it. So I've worked with engineers in the past, including myself a long time ago, who have been hesitant to use algorithms that might not give the correct answer. So I'd like to quickly address the question of when it's appropriate to use probabilistic algorithms. I don't normally read my own slides, but I think this one is kind of worth it. So in testing the primality of very large numbers chosen at random, the chance of stumbling upon a value that fools the Fermat test is less than the chance that cosmic radiation will cause the computer to make an error in carrying out a correct algorithm. Considering an algorithm to be inadequate for the first reason, but not for the second, illustrates the difference between mathematics and engineering. It's kind of tongue-in-cheek, but I think it actually makes a pretty good point. If you can guarantee to a very high probability that you're going to get something close to the correct answer or the correct answer at times, that is generally just as good for a lot of problems. One of the important points is that most of these algorithms have provably bounded error rates. So you're not going to get answers that are wildly wrong, generally speaking. I've never seen a paper on a probabilistic algorithm that didn't quantify or prove the error rate of the algorithm. It's incredibly important, as it's the difference, in my opinion, between probably and probabilistically. And this is the first thing that I would look for if I was trying to evaluate a new algorithm. Bloom filters, for instance, can be very, very useful. But depending on the context in which they're being applied, the input can be large enough and the necessary error rate low enough that they end up not actually being all that useful, for instance. Right, I love this quote. For many problems, a randomized algorithm is the simplest, the fastest, or both. And I would actually go one step further and say that sometimes probabilistic algorithms are the only solution that's actually usable in a real system. All three of the algorithms I'll present today fall into this category. The point at which we were deploying them was the point at which doing it exactly correctly wasn't actually workable anymore. So I guess you could say, like, we shouldn't use them if someone's life depends on it. I mean, actually, that's not true. Many real-world systems rely heavily on algorithms that have a probabilistic component to them, because in fact the data input is unreliable. So GPS navigation systems, missile guidance, submarine guidance systems, they all make use of Kalman filters. Kalman filters necessarily have an estimation component to them because they take several unreliable sources of input and attempt to produce a more accurate output. So yeah, you can actually still use these even if someone's life depends on it. Which is all just to say probably more often than you think. If you consider the acceptable error rate and how that affects the runtime or size of an algorithm or data structure, you should make decisions based on that. I found it to be surprisingly rare that the acceptable error rate for real problems in the real world is actually 0% most of the time. The internet as it exists today has a certain error rate anyway, right? Like NICs die, cables are cut, configuration errors happen, machines burst into flames. Ultimately, it leads to packets and connections being dropped or misrouted. So there's necessarily a probabilistic component to most systems that we actually write. So let's consider the first problem. You want to count the number of unique users making requests to a website. Or maybe you want to count the number of unique objects delivered by your HTTP server. Or maybe you want to count the number of unique IP addresses in a log file, or possibly all your log files. This is also known as the count distinct problem, which is defined as finding the cardinality of a multiset. Or less formally, count the number of unique items in a stream. Okay. So if we use this as an example, here's a log file which I generated. And if we wanted to count the number of unique IP addresses in a huge number of log files, right? In this particular instance, there's 5 unique ones. We just want to count them despite the fact that they occur multiple times, just to be clear about the problem. So the very first thing that would come to mind for me is probably just using a set data structure, right? So you just have a set, you keep track of all the items you've seen, easy enough. It's really, really straightforward to write in Python. Yep. The problem, cool. We can add an IP to it in O of 1. We can retrieve the cardinality in O of 1. But the problem is the space grows and grows and grows and grows, right? So if we wanted to count 100 million unique 32-bit IP addresses, the size of the hash will necessarily be over 400 megs. That's just like the size of the raw data. And yeah, computers have a lot of memory these days, but like this is just one 32-bit field. Right? If we wanted to do this across a lot of things or across a lot of different fields, this would eventually become a problem. So what if we try a slightly less naive solution? In this case, we'll use a Bloom filter. Cool. And then a counter to keep track of the IPs that don't actually collide with anything in the Bloom filter when we're inserting them. What's that look like? Well, it's actually just as straightforward as the last one. We just keep a counter. If the adding it into the Bloom filter doesn't think that it already existed, we increment the counter. Easy enough. Adding an IP, still O of 1. Retrieving cardinality, still O of 1. Great. The space is kind of weird. I can't actually figure out exactly how to quantify that one. But let's say we take an error rate of 3%. Cool. To get an error rate of 3% across 100 million unique IPv4 addresses, we'd be looking at an 87 meg Bloom filter, which is not actually all that useful. If the other data structure was 400 megs, we've only dropped 1 order of magnitude at best. We can do better. Right. So let's talk about hash functions for a second. I think one way to describe a well-designed hash function would be to say it's a function that when given arbitrary input, produces an output that is evenly distributed. evenly distributed in the idea of the bits inside of it, right? And that can be highly useful when you're building a probabilistic algorithm, as we've essentially taken the input and turned it into a series of random values. Now, the last example was Bloom filters, which of course also use hash functions, right? So let's look back at our example. That was one of the IP addresses that was listed there. What can we do with this? Well, let's say we have an 8-bit hash function, which we can feed this IP address to. So what we know about this number is that ideally it is entirely evenly distributed in the space of 8-bit numbers. Another way to say that is that the probability of any individual bit being set is 0.5, or 50%. If that's the case, then you could say that the probability that one particular bit is not set and another specific bit is set is 25%. And if you take that further, 12.5%. You can probably see where I'm going with this, right? So starting back at the top, if the probability that bit 0 is set is 50%, then the expected number of trials until we see that bit set is 2. Likewise, bit 0 not set, bit 1 is set, 25%, the expected trials, 4, and so on. So in this case, the expected trials is equivalent to the number of unique IP addresses until we expect to see this thing. So let's restate that as we expect the maximum number of leading zeros we have seen plus 1 to approximate the log base 2 of the unique items that we've seen so far. Obviously, we can't actually rely on that with a single field. For one thing, we'd only get estimates that are powers of 2, which would be problematic. And for another thing, the error rate of this would be enormous, but it is a start. And this is where the LogLog paper comes in. This is the first paper to describe how to use what we just talked about to come up with a relatively accurate estimation of the overall cardinality of a multiset. And this is the paper that introduced the version that's more commonly known now, which is HyperLogLog. I'm actually going to describe the LogLog algorithm instead of the HyperLogLog version. However, they're very, very similar. The primary difference is really that the HyperLogLog version swaps out the arithmetic mean with a harmonic mean, and it improves the accuracy of a few edge cases and so on. So that's actually a complete implementation of LogLog. It's a really straightforward algorithm. It's about 15 lines of code. So if we walk through it really quick. So when we're inserting a token, we first hash it, we stick that in Y. We extract the k most significant bits, right? Set that aside. Then we extract the remaining bits, right? And then we find the first set bit of remaining, right? And then we index into a list of buckets, which is M. And if the number of zeros that we have seen and stored in that bucket in the past is less than the one that we just saw, we increase it, right? Likewise, the cardinality is even more straightforward. It's basically just 2 to the mean of the buckets, right? So this is that estimation of the log base 2 of the number of unique items we've seen. And so, yeah, you can actually get a fairly accurate number based on this as long as you account for the additive bias. And there's probably someone in the room who can explain additive bias better than I can, because I never took discrete analysis. So, but it's fine. You can pre-calculate them when they're read. So HyperLogLog. Adding an IP, again, O of 1, treatment cardinality, O of 1. And the space, however, is the log of n. So what does that actually end up looking like? Well, for 100 million unique IPv4 addresses, the size of the HyperLogLog is 640 bytes. Not megabytes, not kilobytes. We went from 400 megs to 87 megs to 640 bytes. We dropped 6 orders of magnitude from the naive solution. And this makes it possible to count approximate cardinalities of a lot of different things across a lot of different fields, across a lot of different log files, or whatever you're counting, right? Makes it dirt cheap. Right. So that's HyperLogLog. It's pretty cool. Right, all right, so let's move on to the next problem. So let's say we have a large collection of documents, and we want to find documents that are similar to a very specific one. Or maybe we're finding images that are similar to a specific image. Or let's find graphs that are correlated to a specific graph. There are a whole bunch of different actual applications of this. And this is basically just the nearest neighbor search, which everybody probably knows, which you can define as finding the n closest points in a d-dimensional space. Or informally, you have a bunch of things, and you want to figure out which ones are similar. That's about it. Right. So let's say that what we're working with in this case are documents. Right? A bunch of different papers. We store, let's say, millions and millions of them. Great. Well, the first thing that we need to do is take this document, and we convert it into a vector of some kind. In this case, I'm just using a bag of words type setup. So we lex the document, we convert it into a vector where each dimension is a different unique word across the entire set of documents that we have. And the values of those vectors in those dimensions is the number of times that the word occurs in the document. Right. So if we were going to try to find the similarity between these different vectors, there's a bunch of different ways we could do that. We could use cosine similarity, Jacquard similarity, Euclidean distance. These all have a bunch of different strengths and weaknesses depending on the particular input data set. However, they each all fall prey to the pit that I'm about to walk us into. So let's just say that we pick Euclidean distance. Easy enough. It's really straightforward to implement, and it has some properties that actually make nearest neighbor easier, specifically that it falls into a metric space, which just means it fulfills a few properties, notably the triangle inequality, which just says that for any 3 points A, B, and C, the sum of the distances between A and B and A and C has to be greater than or equal to the distance between B and C. Straightforward triangle inequality. And what that means is that you can use KD trees for this. In theory, you could also use a bunch of newer ones that have been invented, KD trees were invented back in the 70s. And this would work fine if we were talking about a really small number of dimensions. But in this case, we're actually not. And if you attempt to use KD trees with very large numbers of dimensions, it just converges toward linear, right? So you just basically end up doing a full linear scan of the entire thing. And that is known as the curse of dimensionality, which refers to a bunch of different problems that can occur when working with high dimensionality data. I'm not going to go into it here, but it's actually a really fun topic to read about. The solution, however, is often dimensionality reduction, which is finding ways to take the data that we have and reduce the dimensionality of it down to a much smaller, less pain in the ass version. And all these space partitioning data structures that I'm aware of fall prey to this curse of dimensionality. So in fact, for nearest neighbor search and high dimensional data, it's actually approximation is actually the accepted solution that everybody tends to use. So this is where locality-sensitive hashing comes in. Among other things, it is a dimensionality reduction technique. Normally, when we think of hashing, as with HyperLogLog, we think of it as something where even if two items are really similar to each other, they should have entirely different values output from the hash function. LSH is the opposite of that. The 2 points, which are very similar or close to each other, should have very similar outputs from locality-sensitive hashing. LSH was invented back in '98, and it's actually gained a lot of momentum in industry recently, and there are still papers being published about it this year. Can't remember which journal they're being published in, but there's a bunch of really interesting ones coming out in a few months. There's a bunch of different types of locality-sensitive hashes, just like any other hash, and they're each suited for different types of data and so on. The one I've put into production personally is from this paper, which has a bunch of fairly clever LSH functions in there. So my favorite way of thinking about LSH is actually kind of described more or less in this diagram. As a series, think about it as a series of projections. If you can imagine you have a sphere with points placed on the outside of it, and some of them are far from each other, some of them are close. If you were to rotate that sphere in different ways and then project light through it or take a picture of it, you're effectively reducing the dimensionality of that sphere from 3 dimensions to 2. Depending on how you rotate it, sometimes the points that are far from each other will appear to be close, as is kind of the case in the left one there. but usually not. And generally speaking, the ones that are close to each other, when you reduce the dimensionality, will continue to be close to each other. And that's kind of the idea of locality-sensitive hashing. I love that explanation of it. So the one that I've personally implemented is using random hyperplanes. So the idea is that we basically just divide up the high dimensional space into a bunch of different sections, essentially. And once we do that, then we can use that to start estimating the position of the document vectors within that space. So now when we add a new document to our LSH, we compare the new document vector to each of those hyperplanes. Effectively, you can think of it as just like comparing, say, like, is it to the left or is it to the right of the hyperplane? Which doesn't actually make sense because we're talking about very, very high dimensional data. Left and right don't actually make sense in this context, but it's an interesting way to think about it. So the idea is that if it falls to the left, we record a 0. If it falls to the right, we record a 1. Great. So ultimately, what we end up with is 1 bit per hyperplane when you're comparing it to a vector. So if we generate 256 hyperplanes, you end up with a single 256-bit hash for each of the different documents. And now, given that the documents that were similar to each other will usually end up on the same side of each of those hyperplanes, what we can do is just use Hamming distance to determine whether or not 2 documents are close to each other. So just comparing the number of bits in which they differ. And in fact, with this particular LSH, it actually estimates something that's very close to cosine similarity of 2 different vectors. So when I deployed this thing, it was at a previous company that I was at. We had document vectors that had about 5 million dimensions in them. If we were running the cosine similarity calculations ourselves for each of those, it took about half a second to compare those for each document to any other document across, at the time, 10 million, eventually grew up to like 50 million documents. So it's not really a workable solution. When we deployed LSH, it took about 3 seconds to compare a new hash to all 10 million of the other hashes that we had already recorded. So yeah, Hamming distance, super great. The LSH paper has actually contributed a pretty rad data structure that attempts to bucket the hashes to make querying even faster. But the fact is that, like, across 10 million documents with 256-bit hashes, we didn't actually even need it. We could just compare them every time. So that's LSH. Third problem I wanted to talk about. I guess I actually will talk about Fastly again briefly. So one of Fastly's big selling points is that we are able to purge content from our entire network very, very quickly. Whereas like CDNs in the past have been like 5, 10, 15 minutes to do this. We do it in, on average, about 125 milliseconds across the world at a certain percentile. I believe that's like the 95th percentile. So there's a bunch of different algorithms for this. The obvious one that would like come to mind, given that we need to get a single purge from a single location across a giant network of servers, reliable broadcast would be the first one that comes to mind, right? Like, we need it to get there. They generally guarantee that a message would definitely be delivered to a bunch of servers. Not probabilistically, definitely. There's a bunch of different ones for this. There's like SRM and a bunch of others. But, oh no, sorry, I screwed that up. I had cut out a few slides here. Right, so reliable broadcast does have probabilistic guarantees as well. This is not the same thing as atomic broadcast, for instance. So right, SRM and so on. Unfortunately, the problem is that these suffer problems with scale out because they're using a retry strategy, essentially, where, you know, if I do not know whether or not a node has received a particular purge, I would go, okay, here it is again. I'm still not sure if you got it. Here it is again. Here it is again. And over time, if you're trying to scale that up to a large number of servers, it doesn't actually work. Works fine for a small number of nodes, but so then there's a class of gossip protocols. And these started coming out in the probably late 80s and 90s, and they're still coming out today. There's plenty of gossip protocol research being done. Things like Plumtree or Sprinkler, which came out a couple years ago. And these are interesting because they're designed for scale. And the idea is that you should be able to deploy these across tens of thousands of servers and do hundreds of thousands of messages per second through them. And to do this, each of these different algorithms provides probabilistic guarantees, right? So this is different. We're not trying to come up with an answer this time. We're instead trying to come up with a probabilistic guarantee that the message will actually make its way around the entire network, instead of guaranteeing that they definitely will get there. So the algorithm that we ended up implementing for this is called Bimodal Multicast. It's a pretty straightforward idea. We quickly broadcast via a lossy protocol of some kind to all the different servers that we want to get it out to. And then we use gossip to recover the lost messages. So it's a multi-phase sort of algorithm. So the first phase, broadcast, we just send the messages out as quickly as possible. In our case, we use UDP for this. Just like blind, just send a UDP message across the internet. Usually it actually gets there. It's like 99.5 to 9% on a good day. You can use IP multicast if it's available. You can use a carrier pigeon. It doesn't actually matter. You just want to get them out as quickly as possible. Right? The second phase of the algorithm is the gossip phase. So in this phase, every server picks another server completely at random and sends a digest of all the messages that they currently know about. So in this case, A picks B, B picks C, C picks A. So a server looks at the digest that it received and checks if it has any messages missing. Like, am I missing any messages that the server knows about? So in this case, B is missing 3 and C is missing 2. And then the third phase of the algorithm is the recovery phase. So just straightforwardly, every server that received a gossip goes, OK, actually, I'm missing a few. So given that the server who just sent me the gossip knows about it, please send it to me. So 3 phases: broadcast, gossip, and recover. And the neat thing about this is that it tends to exhibit a pretty straightforward epidemic type behavior. So look at this. Again, we started with one node, and it very quickly covers all of them as a little simulation of it. The Bimodal Multicast paper actually includes a bunch of math to predict the percentage of servers receiving a message after a certain number of rounds of gossip. Additionally, it also includes math to figure it out for the case when you're getting message loss as well. So in this case, after 10 rounds, 97% of servers will have received the message that we're looking to send. There is one problem, though, and it's that computers have limited space. Right? So they each need to be able to keep a certain number of messages. Right? However, at a certain point, we have to be able to throw them away, because we do have, again, limited space. So the problem is that in the paper, they talk about throwing away messages after 10 rounds, which, again, is 97% of servers receiving them, which wouldn't be acceptable for us anyway. But the problem is that if we introduce packet loss, this really doesn't work out very well. And we see packet loss all the time because we work on the internet, and it's terrible. So this is the same graph as before, except with 50% packet loss. So we get to 10 rounds, and we see that 40% of servers have received them. That doesn't actually work. So we'll definitely end up losing purges during network outages and so on. So why would the paper end up throwing away digests or rather messages after 10 rounds? Well, the idea is just basically that there is a giant list of messages that you have, and at some point you have to get rid of them. However, it doesn't actually have to be a list. So what we actually do is we send ranges of IDs around. And these are limited to a certain extent in that we will send a certain number of bytes of ranges during the gossip phase, and what this does is it causes the nodes to start recovering from the older ones first, which you can argue about whether or not that's the ideal. But the idea with that is that it starts to fill in those gaps that may have occurred. And so you continuously are reducing the amount of partitioning that happens in that range. So what this lets us do is instead of keeping messages around for 10 rounds or 100 rounds or whatever, we actually keep them around for 86,400 rounds. So, or in other words, one day. Right? So here's the same graph with about 80,000 rounds in it and 99% packet loss. So after 80,000 rounds, we see that we have a 99.999999999% chance of receiving the messages. So this is where, with high probability, is totally fine. This is going to work out just fine. So let's talk about what the system actually does in production, like how it actually behaves. So on a packet, or rather on a link with about like less than 0.1% packet loss, which is fairly normal, we see that the 95th percentile delivery latency is about the network latency. It's basically just one-way network latency. And so in this case, we're showing the graphs from several different POPs that we have around the world, and you can actually tell if that's actually visible, but the idea is that like depending on where you end up sending the purge to, will end up like determining the actual latency of the entire thing. But generally speaking, it's just network latency. So how does this actually behave in bad situations? Well, so here is an example of what happens when we misconfigure a firewall. So this prevented 2 of the servers, B and D, from communicating with anyone outside of their data center. A and C were unaffected. And so you can see there that for a while, the latency for B and D actually spiked quite a bit. They were getting up to almost 10 seconds there. However, if you look at the graph on the right, you see that like they actually continued to receive roughly the same number of purges the entire time. So it was keeping up just by having the gossip inside their own data center. Just randomly, they would occasionally choose each other, and that was actually good enough to recover all the messages that were being lost to those 2 servers. I like this example as well. So here we had extended packet loss happening in the APAC region for multiple hours. It was like 30% packet loss for quite a while. And if you take a look on the right again, no noticeable loss of throughput. The servers kept up the entire time. And one more. This one was fun. So there was a brief period of time when we had a DDoS hitting one particular server, which was impressive. And during the time that server was under attack, it was actually like completely unacceptable. Like it was completely inaccessible to us. We couldn't SSH to it. We couldn't ping it. We couldn't do anything. However, you see that like on the left, the latency starts to spike again, just as we expect. However, as soon as it recovered, on the right, it was immediately caught back up again. So this is one of those, like, despite like the internet being a terrible place to actually attempt to build distributed systems, you can make things that work pretty damn well despite that. So ultimately, the point is that good systems are boring, and probabilistic algorithms can help you to do that. I can go home at night and not worry about having like problems where like I'm having to be paged and I'm debugging distributed systems at 2 a.m. No one wants to be there. So, wow, I ran through those slides way faster than I thought I would. But regardless, that's all I got. So thank you.